Good morning, everyone. Today we will finish first the AASHTO 93. It's a fully empirical design, and I had explained earlier what an empirical design means. That you are directly taking from the field, from the available field test data, you are kind of interpolating or extrapolating. Before that, there were some questions, and I read the questions, and they were very good questions, and I would like to answer them. You have to just, when I'm there, just repeat the question that I'm there. So the first one was, I think if I remember correctly, where do you apply the shift factor, right? Is that the question? Where do you apply the shift factor in the strain equation? Was it applied to the modulus or was it applied to the strain, correct? Is that the question? Okay, so I'll answer that question. It's a very good question. And I'm glad we are getting these questions on I'm glad we are getting this question about the model, because the model is the linchpin of the entire mechanistic empirical design. So what I had covered yesterday was you have one data set, NF of field, right, based on the accelerated pavement testing, correct? So we did that. We have one number for a given mix, correct, and section, right? And then what we did was, this is for one section, right, and one combination of one pavement section with one combination of materials, correct? So we had identified that one NF of field is available, and remember the NF of field is determined when you take the pavement performance and compare it with the criteria, right? And the criteria depends on safety. So one section and one combination of materials, and you get NF of field right there. Okay. When I go in the lab, okay, and I have an F with strain value, right, and micro strain, you get this curve, right? So you are applying this. So this is just NF of lab, all right? And now you are taking the NF of field, it can be up or below, and I said that this is matching. This micro strain, strain in lab is equal to strain in field. There's only one condition where both are matching, correct? Okay, so you have NF of strain, and right here you will have NF of field. Got it? Right? And this is what you apply. So the question was, do I apply the calibration factor on the strain equation or not? You will apply this on. You will initially apply this for a given E value, for a given E1 value, right? And therefore you will get NF is equal to K1 epsilon T minus K2. Correct? Now when you do multiple tests, okay, of the same of different moduli, all you have to do is, so this is already calibrated and for a given mix, right, for a given E. And then when you add that, NF is equal to K1 epsilon T minus K2, all you are doing is adding this coefficient to this model. Does that make sense? So you are only calibrating on the strain equation, and then you are adding it to the modulus equation. That answers the first question. Can you read the second question? Does that answer it? Can you check?
Yes. The second question?
Yeah.
I'll ask. In the fatigue distress model, how the elastic modulus was included? Did they conduct laboratory tests with the multiple elastic modulus samples?
That is correct. You have to do multiple tests, right? So if I take this, the given section as one combination material E1, you have to do lab tests of different materials, right? So you have to do E1 prime, E2 prime, different mixes, right? Different mixes have to be tested, and you will get a different equation. But Just to remember that this was not constructed right in the field, right? There's only one, so you can't calibrate that, right? There's only one calibration suitable for one even value. You just have to tag on a different even value. Yes, you have to test different mixes, have to do beam fatigue tests at a broad range of strain values.
So third question is the final calibrated fatigue distress model was calibrated against certain categories of materials. So if we start using various other materials like SMA, does that calibration factor does get affected?
Great question. So the short answer is yes, it does get affected. The question here is how much you are willing to invest. There is okay. How do I? So there is enough factor of safety embedded in these designs to account for a broad range of mixes. So when we go into pavement ME, you will see that some of these mixtures will need a recalibration, but in the long run, the the difference is going to be so minimal that you should be absorbed. You should be able to absorb that difference, if that makes sense. So the correct theoretical answer is yes, it has to be calibrated. That's the, but it costs money. Correct? Everything costs money. Right? So if I go about and do SMA mixture, like make a payment section, if I'm willing to do that, fine. Right? Good for us, right? But all of this takes away from some other resources. So then you have to be very strategic. Okay, does it really matter if I increase the air voids, added polymer modified binder? And just this is a very good question. So for example, HMA, hot mix asphalt, my E1 value for a given temperature changes from 100,000 to let's say 500,000 in a given temperature range, PSI. Right now, SMA might change, right, E1 from let's say 80,000 to 450,000 in that range. Okay, correct? It's a different mix. The only thing payments need is E value. Now, is this a big difference? Right? For this particular difference, do I invest so much money to recalibrate? That's a strategic decision that has to be made. Does that make sense? Right? So if your model is able to absorb as many changes as possible, the better it is. Right? Otherwise people will get upset. Oh, people will be afraid to do innovation. Oh, one more mix, now I have to recalibrate again. Who is going to deal with this? Does that make sense? So your model has to be robust enough to take a broad range of mixes. Excellent question.
The last question is, similarly, the way we have calibrated the lab fatigue equation with respect to the field fatigue data, let us say if we consider any test method like a wheel tracker in the laboratory, it also has some specification criteria and a corresponding loading cycles in the laboratory for a particular loading condition. How was this has arrived, and if can give some details in this regard?
Very good question. All right. The question is a little more philosophical, but a very relevant question. There are many lab tests in the world. Many. Wheel tracker is mentioned, and so many more. APA, Hamburg wheel test, beam fatigue test, ILCT, SCB, you name it, there are many cracking tests available. So you have a lab performance test, right? There are many, correct? So you have a lab performance test which is done in the lab. Fair enough, right? So having recognized that, so the question here, I understand clearly the question, how was the criteria developed, correct? That's the question. How was the wheel tracker criteria developed? And I'll answer that question. So let's say a lab performance test, this tape looks at the wheel tracker, right? So wheel tracker test, and now I want to test this. I can't remember what you guys test this at. I will just give a number, 40 Celsius. Let's say you tested at 40 Celsius. Fair enough? So it's a wheel tracker test. I do that at 40 Celsius. the question will come, and I ask my students all the time, any lab test I pick for my study, there is a reviewer out there that said, why didn't you pick the other 9? All right. Why did you pick this? Right? Well, because you are going to make your entire results based on this test. It's not a magic test. Remember, what is the right answer? The truth is out there. Right? I said that yesterday too and day before. The only truth is the cracking happening on the roadway, the rutting happening. Nothing else is the truth. Everything is a representation. Everybody with me so far? So having said that, if I were to take a wheel tracker, right, and I want to make this meaningful, really meaningful, right? What I need to do is take 20, 30 mixes, right? Take around 20, so I'm just giving a number 30 mixes. Let's say I have to test this in the wheel tracker. Okay. Construct the pavement. So those pavements, not in the accident pavement testing, because that costs a lot of money. So you put it in different parts of the state, right? So you have 20 to 30 mixes, construct them on actual roadways. Now this is a very complex problem, right? When I do that, right, my section, rest of the section has to be similar, right? I cannot have different cross section because the performance will change, correct? So this is not an easy problem. So let's say I managed to do that. So I have 20, 30 mixes, different mixes. I did the wheel tracker test and I construct them on the roadway. Everybody with me so far? Now I get field performance, right? So I get field performance of these. And I get rutting performance of this at the surface. And I do wheel tracker 40 Celsius independently in the lab. That correlation is the best way to identify the criteria. So wheel tracker and rutting performance, so you have rutting in the x-axis in the field, millimeters in the field, right? And you have wheel tracker, right? And rutting, correct? And now this is going to be the correlation. Fair enough, right? It won't be a straight line, it won't be a clear cut, but give or take. Now I have my criteria, right? Failure criteria. Remember, the failure criteria is always on the field. And now I come back, and this is the lab failure criteria. So this question comes up all the time, and it's an excellent question. How do I take a lab test and identify what is the failure criteria in the lab? If you are doing anything other than this, you are faking it to some extent because this costs money. I'm not judging anything, but it is an expensive proposition. But people will come and say, I don't have the money to do this, but I need to determine the criteria. Right? So what people do is be very strategic. They go to different states, different countries, get mixes, and try to test something like that. They try to leverage the data from all over the world and try to get this, but nothing is closest to the field. Does that answer the question? Any other question? Good.
Yes, thank you.
All right, let's go to AASHTO 93. I'm going to go do this without the slides because I think this slides are more confusing than it should be. I'm going to do it as if I teach my class on AASHTO 93. I will cover that. I just kept my notes so I don't forget the hard numbers that I need to remember. But other than that, I should be okay. Let's look at this. AASHTO 93. This is completely empirical. There is no model. Remember, AI was the mechanistic empirical model. There's no model here. This is completely statistical astropyramidism. I'm going to go through some of the factors, some of the requirements of this. Okay, right here. First thing is the design life. right? So that you need to implement 20 years, whatever it is, right? And from the design life, you will get your design list. We already went through this calculation. You will get your design list. Fair enough? We did this calculation also. So you 20 years, 30 years, 10 years, 15 years, whatever that is, and you can do that. Next, this is important. Your target performance. That means you have to design. So if I say that payment has to last 20 years, what does it mean? What does that statement mean? Right? It has to mean something, right? Last what? What does it mean? What that means is that my change in if my change delta PSI, I covered PSI yesterday, right? So if my change in PSI in 20 years has to be not lower than certain number. That is my criteria. There has to be some criteria, right? So delta PSI you have to identify has to be, I'm just giving an example, 5 to 2.5, let's say. Right? So in my 20 years, I start from 5, and by end of 20 years, it should not be going lower than 3.5. Fair enough? Right? So that's my, remember I call you damage. There's some amount of damage done, right? And this is very powerful because we remember we correlated to rating, payment subject to rating, right? So the delta PSI is 2.5 in this case. Fair enough? The change in drop in PSI. So what you are telling the design is that in my 20 years, I don't want the delta PSI to drop by 2.5. Next. Reliability. Reliability is what risk I am able to take. Okay. So this could be 90%, 95%, whatever it is. Okay. And I'm going to explain this to you. So basically what this means is that if I increase this number, right, what I'm telling you that with all the uncertainty of my input parameters, I know like my variability in traffic, variability in material properties, variability in many places. Considering all the variability, if I take only 10% risk of failure, what should my design be? Understand this thing really clearly. So remember, there is a lot of variability out there. There's a lot of unknowns out there, right? And now, but my client wants me to last 20 years with delta PS of 2.5. All right. So if I bump this up to 95%, 5% risk, or 99%, what do you think is going to happen? Anybody online here? So if I take 1% risk versus 10% risk, what will the design tend to do? Cost, yeah, you will make the design conservative, right? You will start to put that subgrade away from the load. You will start to put stronger, thicker and thicker and thicker materials, right? You see what I'm saying? So that's the tendency. So I'm going to give you the theme here, right? The AASHTO was done in 1950s and 60s, right? Now we are 2025. So everywhere there is an inherent factor of safety being added all these places. Does that make sense? Okay, if I go from 90 to 99, all those thicknesses will go by a couple of inches. Correct? What did you do? You pay the price, but you're absorbing, you're reducing the risk. Fair enough? Any questions? Right. This is very easy to do in the design, but I want to understand what each of them mean. There is a reason behind each of those things. Next is standard deviation. And there are two numbers, right? Flexible S0 is 0.45, rigid S0 is 0.35. I'll explain what that means. When the AASHTO design was done, remember that yesterday I gave the explanation of the 10 sections, right? So there was variability in the mixes, there was variability in the soil, all of that stuff. What they did was, they kind of did they gave a aggregate number, one single number looking at the standard deviation of all the properties, if that makes sense. Okay, so it was a very strategic way that for those sections, whatever that number was, for flexible pavement, asphalt, it was 0.45. For rigid, it was 0.35. So asphalt is more variable than concrete. Therefore, that number was that. So it was like a made-up number, but it accounted for all variability that was done. And probably the next class I'll explain how it turned out to that number. But for now, as long as you understand that this is capturing the variability of the input parameters and all the other variability coming in. Next one. Delta PSI 0.45 and 0.35, that is correct. Now I'll explain. Can I move on? Now, structural number. Very, very important concept. Right here. Let's look at a single layer, natural soil, MR is given here, right? Protecting the subgrade. I'm going to look at one single layer. I want everybody to think. So right here, I want to protect the natural soil from the load, correct? For the given environment and climate. I've said this multiple times, correct? What is the way to do it? Yeah, so there are two ways of doing it, right? Or multiple ways of doing it. One is increase the thickness, right? D, right? Or make on decreasing the stress and load. Yeah, so you decrease the stress and load, or you increase the E, or the combination of it. Fair enough. So what this structural number is doing is that it is a fictitious number. It's a fictitious number that takes this and converts this to something called a layer coefficient. So it's equivalent to material property. Just take it as that. So what it is saying is that my structural number is a structural coefficient which is a function of E, which is a property of the E, of the material property, times the thickness. So what it is recognizing is that if the job of the pavement is to protect the subgrade, I have two tools at my disposal. Thickness and property. It is recognizing. Correct? Everybody with me so far? Now, two things. One, subgrade. Okay. I'm protecting the subgrade, right? So, structural number required to protect the subgrade is called S and required. I'll explain that in a minute. Okay. So what that means is this. If my MR is 10,000 versus my another MR is 5,000, 2,000 let's say. Which one is weaker? Very obvious, right? 2,000 is weaker. What is the structural number required to protect MR of 2,000 is going to be more, or of 10,000 will be more? 2,000 will be more. I will need more structural number to protect an MR of 2,000. Fair enough? That's the basic concept. If you understood that piece, that means the structural number required is always the layer below it. So, you know, this floor is falling apart. What is required to protect this floor depends on the strength of the floor, right? Not what is protecting it. So, what is the biggest mistake students make is that they say, oh, structural number required depends on this. No, structural number required depends on this. Structural number you provide depends on this. Can everybody see the difference? All right, everybody with me? So if the structural number required to protect MR of 2,000 is 7, then I have to provide more than 7. Fair enough? If this required 4, then I have to provide more than 4. So can you see the difference? As long as you understand this, the thing becomes okay. Let's keep going. Trying to find the easiest way to go through this for you guys. Right, let's go to the next slide, then I'll go to the next. So, all right. We'll open the textbook. Yeah. All right, you're ready. Rotate this. Okay. Make it a little bigger, maybe. All right, I'm going to explain this in detail. Then I'm going to go to all the colors. All right, I'm going to explain this graph to you. And in my next class, I'll explain how this was, next lecture, I'll explain how it was developed. Right? Right here. Okay. This is the chart to get Sn required to protect the soil. That's the chart, right? It's an equation, but it is done in a very simple form. And I passed the equation, but let's go with this again. Okay? I'm going to explain each of the input parameters in detail. One is reliability. I talked about reliability. In this case, is 95%. Right? So that is the risk. 5% risk I'm taking. Okay? Then the standard deviation, 0.45 right there. That's the overall variability. You draw a straight line and you come to something called a turning line. Everybody okay so far? Then you go from here and you hit the design essence. That's the one we calculated yesterday. Right? In this case, it is I think close to 4 million. I think, right? So 4 million essence, right? And you come to the other turning line. Everybody. Then you come down and you hit the subgrade modulus, the one you are protecting. Everybody, the one you are protecting. Then in this case, it is 5,000 psi. Right? You come down here. Do not continue through the box. Stop right there. You make a horizontal move till you hit the delta psi. The delta psi is 2.5, right, in our case. And then you come down and the structural number required to protect that subgrade is 5. Everybody understood this, right? Everybody got this? That is all the time to get Sn required to protect the layer below it. Everybody got it? Let's do a simple exercise, okay? So I'll go one step at a time, okay? So I Oh, I did not take it there. I hope they heard me. I had forgot to take this there. They heard me, right? It was okay? Yeah. Okay. Right here. So, now this is the case. So for this, if I keep the properties same as this, right? So now using this conditions, right? So my Eason's W18 is at, what did I say? 5 million? 4 million, give or take, right? Right, give or take, right? Based on that sheet. And MR, how much? 5 years, correct? Fair enough, and everything else is the same, right? That's as you can see. So now I got SN required to protect this MR is 5. So now I have multiple ways of doing that, right? I can do one layer, I can do multiple layers. Fair enough. So let's do one layer at a time, just to make it very easy. A1 times B1, and that is W. Just one single layer for simplicity. Then I'll do second layer, third layer, fourth layer, and the concept is similar. So right here, I have to get the A value, right? A value. So I will go there. I will go up here. By the way, the equation that you have plugged in is this equation right there. The whole nomograph that you saw, and it's very fascinating when you go back and see how they came about developing this. Is like phenomenal, right? Like the brilliance of those people in the 50s and 60s who cared about this. So that's how they came up with this equation, and the world is using it, right? After 60, 70 years, and payments are doing okay, right, in general. So. I'll come back to this in a bit, right here. So A value, this particular figure 11.27, if you want to write this down, right, we'll have to go back and forth. Figure 11.27 gives you the A value of the asphalt. Okay, gives the typical A value for the asphalt for a certain resonant modulus. Okay, so A of HMA, correct? So let's say if I look at this, and the HMA modulus, let's assume that the HMA modulus is what number can I 4, right? So let's say if the HMA modulus is 4 into 10 raised to 5, right? PSI, correct? And the A value from figure 11 what is the number? 27. 27. Right. And what is the A value typical approximately? 0.41. Thank you. 0.41. Let's give it. Fair enough? So very simple, right? So Sn, my Sn provided, how much am I providing? A1 times D1, correct? A1 times D1 is what I'm providing. Should be greater than or equal to Sn required. Fair enough? It is very important that I keep this terminology because books don't provide that and it creates lots of confusion. You know, what is what? So Sn provides A1, D1. A1 is 0.41 times D1, I don't know, greater than or equal to 5. Right? That's what we got from the previous Sn required 5. Yes? From the nomograph. So my D1 should be greater than or equal to, what is this number? 5 divided by 0.41. Anybody can give me a number? What is it? 12.2. 12.2, right? 12.2 inches, and I will round it up to the next half inch. 12.5 meters. That's a design. That's a simple design of your single. You have solved the problem. This has done. I want you to clearly understand. Oh, it's so easy to plug in. But my job is to show the brilliance behind that equation. Even I can do this math, right? But like, okay, what it took to develop this equation to understand, to look at converting E to A value, right? And structural coefficient, something very simple numbers to handle the design. Now, let's take the same problem. Let's take the same problem and divide this into multiple lanes. Fair enough. So now I don't want to do one, right? So I want to do multiple lanes. A1, D1, and then A2, D2, and my MR is 5000 PSI. A2, Z. Now I am dividing into two lanes. Fair enough, right? E of the HMA I already told you is 40,000 PSI, right? From before. 400,000, right? Good. Let's assume the base layer you will provide. Let's assume that E is equal to 20,000. Let's say. That's what you know what is available in the table. Fair enough? So now there are not one layer, two layers now. I have to get D1 and D2. My job is to protect the subgrade. Got it? Now I know SN required to protect the subgrade is 5. We already did that, right? Fair enough? But I don't have a unique solution. I can provide by multiple ways. I'll get the number 5. Right? Because A1, D1 plus A2, D2 should be greater than 5. Fair enough? So like the whole thing has to be greater than 5. SN provided A1, D1 plus SN provided A2, D2. But how do I do this? So you start from top to bottom. Right? So right here, what is my SN required to protect this number? Number. Right? So my SN required to protect the base, I have to calculate first. Will it be more than 5 or less than 5? Will it be more than 5 or less than 5? Less than 5, it is stronger. I just discussed it earlier. So it will definitely be a number less than 5 because 5,000 is less than 20,000. So my SN, so you have to go back to the nomograph that I showed you and you have to go through the whole process and get the SN required to protect this base layer. How many layers are there to protect this? How many layers are there to protect this base layer? I'm asking you a question. How many layers are there? How many?
2 layers.
One layer. Only one layer. This one. So now there's only one unique solution, correct? So everybody with me so far? Alright, let's start this. So let's say I went through the nomograph, from nomograph, right? SN required to protect the base, let's say, is 3.5. I'm not going to go through that, right? You understand the process, right? So you have to use a let's say, right? Everybody understand that? I'm not going to go through the process, but you have to go through the process, right? So SN required to protect the base is so much. So SN provided should be greater than equal to SN required to protect the base, correct? Fair enough? Right? So SN provided is only one layer is kept, correct? A1, D1 should be greater than or equal to 3.5. Yes? And I know what my A1 was, 0.41, right? So A1 was 0.41, right? So D1 should be greater than or equal to what?
Eight point five.
8.5 even?
Even.
What, exactly 8.5?
8.53.
5.4. So I have to round up by half an inch, 9 inches. I can't go less. I have to go and round up, right? So D1 is 9 inches now. Remember the number first. How much was it? 12.5? for the hot mix asphalt from the previous number? Now I have to find this D2, correct? Everybody will be so right? Now Sn provided to be greater than equal to Sn required to protect the subgrade. Fair enough? Now I have two numbers to protect, A1, and I'll call this one as D1 asterisk. This is what I actually provide, 9 inches, right? I've rounded it up. So A1 times D1 asterisk plus A2, D2 should be greater than or equal to 5, yes? Right now I have two layers to contribute to 5. Now I can go multiple layers, right? I'm just showing 1 to 2 I mean. I have to find D2, alright? I have to get A2. With me so far? Let's find A2 and then we solve it. Right here. A2. The equation is right there. The equation is right here. Okay. For untreated and stabilized base, A2 is 0.249 log E2 minus 0.977. Got it? Right? That's why I already gave you the E value, correct? 20,000 psi. Right? For untreated, unstabilized, stabilized and base coast, right? And then I go down, and if I'm using it as a sub base, there's another equation, A3 is equal to this. So if I'm using 2 layers, 3 layers, you use accordingly the right equation. Got it? Everybody with me so far? Right? So, and you remember this from last time, right? A1 E2 is equal to K1 theta K2. We talked about the stress invariant. It's granular material, no cohesive. As you increase confinement, your modulus goes up. Alright, let's plug it in. Can you please plug this in for me? Those online. A2, can you calculate A2 for me from E2 equal to 20,000?
So is there any graph to find out the A2?
This equation.
By only this equation.
Only this equation. Alright. So only this equation you have this one. So 0.249 log E2. Can you plug that in for me? And then plug it in there and get me D2. Plug it in here and you get me D2. It's not a random number. There has to be only one correct answer. Everybody good online?
A2 is 0.093.
Anybody second that? Anybody second that? 0.093? Natural log, no, log of 10 of 20,000 times 0.249 minus 0.977. I don't have a calculator with me. Anybody online? Confirm it? 0.093? Seems too low. But you may be right. Is it right? 0.093?
Yes, I calculated
0.093. Okay. So plug it in. A1 times D1, 0.093 times D2 greater than or equal to 5. Using log of 10,
So
right?
somebody said 0.094.
So 0.093.
0.093.
9394. Okay. That's depends on it. Alright. Sounds
Sir,
good.
Ujjwal Solanki is asking what is our E3?
Okay, we don't have E3 in this problem. So I can, if I give you a problem with another E, then there'll be E. Right, I3 it, right?
Yes.
Yeah, exactly. So I'm just going one step at a time. Right? I'm just explaining the concept. There's no, so you can do multiple layers as you can imagine. So let's finish this problem up. What is this? What is the D2? Anybody got the D2? Anybody got a D2?
284 hours.
कितना?
284.
284 inches.
अभी ऐसा एक मिनट देख लेता हूँ.
You guys put this as 20,000, right? Not 2,000, correct? Right. Okay. All right. So A1 is 0.41 times what is B1? 9, right? Plus 0.093 times D2 has to be greater than or equal to 5, correct?
Right.
And what is your D2? 14.56. I round up to the next half, 15, right? Fair enough? So I have my answer would be 15 inches of this and 9 inches of this. Got it? What is my previous answer? Do you remember? 12.5. 13, right? 12.5 rounded up, right? So that makes sense to some extent, right? If I took full hot mix asphalt of 400,000, I need only 12.5 inches. Right? Now I substituted that with 20,000 and now it became 24 inches. Again, it's a cost optimization problem, right? Both will protect the subgrade, both will should theoretically survive all the 20 years. Thank you, sir. Should survive 20 years of delta PSI of 2.3. Does that make sense? Good questions for me, right? So you can now, this is the AASHTO design. Does that make sense? So you can do any combinations of any of those cables. Questions for me? All right, I'm going to explain some very important concept about damage due to freeze fall. So that's your subbase. If you have a third layer, you have your subbase, correct? Right? And I'm going to just finish this part really strong here. One. You do layers right here. This is another factor of safety, which AASHTO has done. Look at this. Figure 11 point table 11.21. Minimum thickness of asphalt and aggregate base. Okay. So depending on your traffic level, right? So if you have 500,000, they can hear me, right? 500,000 to 2 million, minimum is 3 and 6. What it is telling you, I don't care what calculations you got. If you are at this traffic level, these are the minimum numbers you have to provide. So immediately, again, level of factor of safety. You see what I'm saying? So every time they are worried that I am extrapolating this data set beyond that requirement, and so again, if you have greater than 7 million, right there, 4 and 6 inches minimum, they will provide. In your case, it is very high, 9 inches, because you have very weak subgrade, but many times you will not see that. Okay, that is one thing I wanted to explain. Oh, this is very. All right, now I'm going to cover something called. I already covered this graph, nomograph. All right, I'm going to explain this to you, which is looking at daily annual change in modulus value. The concept here is phenomenal, very, very interesting right here. All right here, in January, this is the soil. This is just the natural soil, right? Remember, I went with a single number, right? 5,000 PSI, right? But in reality, through the entire year, the number is not going to be the same, right? And we talked about balancing the risk. This table helps you get to that final number of whatever I use in my design. I'm going to repeat. This table, I skipped this step in the beginning because I wanted to explain the structural coefficient. But the question comes, okay, you came up with MR of 5,000 for the entire 20 years. How did you come up with that number? This table will help you get to that number. Is that clear? Let's look at this. Right here, January, which is 15,900, right? Very cold, right? This is again US system, icy. February gets even colder. March, April gets frozen, solid rock. Freeze thaw happens, right? Suddenly becomes warm. Water is soaked in, cannot escape, drops to 900. Everybody with me so far? This will be real data, right? Now there are two data sets. Basically, you depending on how much money you are willing to invest, you can get the data for the first 15 days and the second 15 days. You have more money, get for every day, right? Everything costs money, right? Depending on how much money you have to collect the data, right? So this is just telling you they have given two rows for 15 day data. That makes sense. Now you keep going up, 900, June, July, August, September, October, slowly water dissipates, and now that number is coming up. Got it? And finally you come back to 45. Okay, everybody with me so far? Now this is the they came up with something called damage. Okay? What it is saying is that if I constructed the payment with 15,900 modulus, and that was there throughout the year, every time, the damage cost would be, is a made up number of 0.02. It's coming from this equation, 1.1 times MR raised to minus 2.3. It's an equation plug-in. Everybody with me? Got it? Everybody got it? So yeah.
Actually, sir, in the previous model, sir, AI model, sir, damage was based upon the PSI and PSR values.
Yes.
So there, what is the criteria for damage?
Such a good question. So it is exactly based on the PSI and PSR. So it is just a made-up number to look at if I have this resonant modulus of 15,900, right? If the damage caused by, if I go back up here, just a second, right here, right? So so basically what it is saying is, what it takes that if I have, what this does, right? I'm going to give you a simple example of this. If I had this modulus, right? And if I have a sudden repetition coming on that modulus, a damage caused would be 2%. Let's give it a number because it's 0.0. But the same loading, if I had 900, would be 1652%. Right? So that the damage will be so many times more if that payment was weak. That weak. So it is almost like number of cycles to failure. Almost like the damage is going to like, it will cost so, it will fail much later at 15,900. It will fail so many times quicker at 900. Yes, this is a very good question, right? Does that make sense? So what it is doing is that it calculates the relative damage it will do for a given modulus, right? Now, it takes the average of the damage, not of the modulus, of the damage, okay? And it says the approximate damage is 2.11. So what it is telling you is that I want to clearly understand the concept here, that if in the entire year, right, some days there is absolutely no damage, some months, sorry, no damage. Some months it's like brutal, right? But the overall damage was 2.11 for that year, for that given year, right? So what is that modulus? If I assume the modulus to be the same through the entire year, what would that modulus be to cause the same amount of damage as if this was occurring every month? We'll repeat, right? I want a single modulus value that will cause the same damage as this distribution would cause. Can you understand this very clearly? So if I back calculate this, that number happens to be 2200. So what it is saying is that if I took 2200 every month and kept it constant, it will cause exactly the same damage of 25.30 overall. Fair enough? That's a simple matter.
But sir,
Yeah.
is this practical, sir, to keep 2200? In the real world, sir, it is not practical.
It is not practical in what sense?
Sir, like in the month of May, sir, due to excessive thawing action, sir, see the damage is relatively much higher.
It's a risk we'll have to take. So that's a great question. If I start going for the lowest number, I will tend to overage. You are minimizing, you are balancing the risk that overall damage will be the same over the year. So yes, I have another opportunity that 20, but think about it the other way, right? Think about it for a second. I'm going from 38,000, 50,000 to 2,200. Instead of looking at the other way, oh, I'm not doing 900, but I'm not taking the average of those numbers. If you try to average them, it will be much greater than 2,200. So you are almost very close to 900. Does that make sense? So you have this 900 is pretty much dictated this number, like it or not, right? Does that make sense? I'm dropping from a high of 50,000 to 2,200 because of one single number that is just dictating the damage. Now, will I? State agency could say, oh, you know what? I don't care for this number. Let's pick the lowest one. Fair enough. So much more money we'll have to spend. Does that make sense? So that 2,200 number is what will go here when you do the structural number. Is that clear? Got it, everybody? Am I covering all concepts here? All right. Any questions online? Anything online? Anything that I've not covered, I'm trying to go through this. I talked about reliability, I talked about the coefficients. I'm going to look at anything else in my notes that I've completely missed. I have some very good concept problems here, which is tempting for me to ask. But I do that. So I'm just checking really quick if I missed anything. Yeah, I think I covered in terms of, okay, one more thing. Let me give you a thought experiment, because I have a few, how much time do you have?
So half an hour.
I have half an hour. I want to give you a thought experiment right here. And usually I do a project with my class where they have to optimize cost as well as this, but I'm going to just phrase it in terms of questions for you guys and see if you can answer it for me. Okay. Let's say the entire structural number coefficient, right, works on 1, E2, E3, right? Simple 3-layer for now, right? And it overall works on E1 is the strongest, E2 weaker, right? We discussed this several times. But that is not going to be the case many times, right? So my question to you is this, right? If I see E1 is the hot mix asphalt, right? And you happen to have a cement stabilized base, just happen to be in this particular section, right? It's an old pavement, it's a cement stabilized base or bituminous stabilized base, something like that, right? Lime stabilized base. Now that has a very high modulus, almost semi-concrete, right? And you will get, let's say, E2 of 500,000. Fair enough, compared to 20,000, right? Very simple. And now the subgrade is going to be same as 5,000. Let's put the same number, right? Question for you. If I start doing the same logic as before, right? SN required, SN provided. So SN required to protect this 5,000 was what? How much was that number? What was the SN required? 5, right? Fair enough, correct? But immediately if I do SN required to protect this, what will happen here? Less than 5. Definitely less than 5. What actually might mathematically happen? It is going to be less than 5. What is going to mathematically happen? You are almost going to see, like, you will not need any thickness at all. Correct? Does that make sense? Because it is just, this is so strong that it will, this SN provided by this may be greater than 5. If that's my point. You see what I'm trying to say? Right? So you will end up in a position like very confused. Oh, what happened there? Do I not need the hot mix asphalt? No, you need the hot mix asphalt. Right? It's just that mathematically, it is forcing you to say that this is not needed. Is everybody with me so far? Can everybody see that? I'm not going to plug in all the numbers and do that thing. People will start seeing almost negative numbers. They go, I don't need this thing. HMA is negative, right? But you will have to use your logic. Okay, then what will dictate this minimum requirement? So you will almost get in decimal points, right? Because this is so strong. You will say EHMA needed will be, I don't know, 0.1 inch. Nobody points 0.1. So what will dictate? What will dictate? I showed you the table there in the textbook. The traffic level. Remember I showed you the traffic level? 6 million, 7 million, 8 million. That traffic level will dictate. So remember I showed you 7 million. This was minimum 4 inches. Correct? You saw that AASHTO table, right? I remember that number. So you will end up, so that is exactly what AASHTO is doing, is that, you know what, if 7 millions, I told you minimum 4 inches, right? This is very strong. Ignore your math, right? You will have to provide minimum 4 inches, even though this is very strong. Again, you are protecting the natural soil. You are just taking the risk that I am going to make it very conservative because the traffic is so heavy. I just don't trust the math. You see where I'm going with this? So that is the industry has recognized that the empirical design has run out of its utility, right? Does that make sense to you? So this is the things you have to know that the minimum will dictate as you go through that. Couple of things. When I do the cost optimization, many times you will be locked by the grade of the roadway. Right? I cannot increase the height of the roadway. There's a bridge coming over. So I might be locked at this entire distance cannot go up by more than 4 feet. I'm locked by that constraint. Now you have one more constraint there, right? You have to excavate, you have to remove the soil if I need a weaker soil. There's a cost to that, right? Or I provide a better material. So there's multiple optimization problems that if you guys are interested, I can share the problem with the group, but then we don't have the time to do that. But you guys can do it, on your own. It's a very fun problem where I provide the constraints, realistic constraints, cost constraints, and then you cost optimize, and of course, making sure it lasts the traffic. That makes sense to you. So if I lock you to 50 inches, right, and you provide a very weak subgrade trying to save money, right, 10,000, let's say, you will end up having 60 inches. Can everybody understand that? That means I have to excavate how much? 10 inches. Correct? Right? I have to excavate 10. That's a cost. I have to take the material out, I have to haul it, and so on and so on. Questions? Any questions online? Good. So I covered, so the equation that I covered, log W18, that is that nomograph, right? I covered that. And then, right, this is the development. So, oh yes, I have to tell you one more thing. M2 and M3 are drainage coefficients. Good enough. Looking for M values, just give me a second. There's a M values in the table. drainage coefficients any value. No, I don't see them. There's one more thing I will cover. There are two more concepts I'll cover right here. Delta PSI. That's the delta PSI is the change in serviceability index. Okay, and that is due to a couple of things. Okay, one is traffic, the drop in serviceability due to traffic, and delta PSI due to long-term impact of environment. Okay. So we discussed earlier that the delta PSI drops from 5 to 2.5, correct? So a drop of delta PSI of 2.50, right? So what happens is that if the total drop is 2.5, there will be a drop due to traffic, and if I theoretically close the roadway to traffic for 20 years, there will still be a drop in delta PSI. There will still be cracks formed, there will still be sweep. So that is your delta PSI of swelling, delta PSI of frost heave, and that is the total delta PSI due to swelling and frost heave. And that is around 0.8. You can see. So over the 20 years of time, right, they estimated that this is long term. Short term is due to subgrade. I just did the short term due to subgrade for the 1 year, right? But the long term, over a long period of time, without me having any traffic, there will be a loss. So this summation, the summation of these two is the total delta PSI. So this is one way to account for long-term impact of environment. Swelling, frost heave, soreness. Got it? So I wanted to bring that up. But it is already embedded in the 2.5. Nothing changes. As long as you recognize, if this happens to be 0.73, then 1.8 something is for due to traffic, and 0.7 is due to long-term durability. Does that make sense? Give or take. So a lot of effort has been made to account for every factor. Does that make sense to you? Everything is accounted for. Okay. Does that make sense? Next one. I cannot find the table of the drainage coefficient. It should have been there in the textbook. But let's look at this. Drainage coefficient is defined by M. And his ability to remove water from the gauge. Okay. So what it is saying is, if the layer holds water, it is not as good. If it is a base, sub-base, if that layer allows the water to go through, remember water is the big problem, right? Freeze-thaw problem. So the ability to remove water. So if this increases, ability to remove water increases, my drainage coefficient increases. That means it is, so now structural number provided is given by A1 D1 M1, A2 D2 M2 plus A3 D3 M3 and so on and so forth. Remember previous one there was no M because but there is another factor accounting for drainage coefficient. Okay, and the better the material to remove the water quickly, this M value goes up. That means it is stronger and stronger. The more the ability of the water layer to hold water, the M value drops. So it will become 0.8, 0.7, 0.6. Immediately it will drop the utility of this thing. Does that make sense to you? I wish I could find the table. It's in the textbook. I'm not able to find it, but I'll open it up. Everybody with me so far. So that is another way of accounting for water drainage in that system. So SN provides A1, D1, M1, A2, D2, M2, and M3, and this depends on this, and there is a table to look at. I think I'll find the table right now. Right here. A1, D1, A2, D2, A3, and M3. Right there, right? And thank you.
Yusuf sir,
Yeah.
good morning.
Yes, go ahead.
Yusuf sir.
Yes.
Okay. Yes, sir. Yes, sir. This cumulative serviceability loss due to environment.
Yes.
Hello. Yeah, audible, sir?
Yes.
So, how this serviceability loss due to environment can be considered in Indian condition?
Yeah, absolutely it can be conditioned. So,
Yes, sir.
yeah, you should be able to look at loss of serviceability due to frost heave in this region. Absolutely. So you have freeze thaw happening all the time. You have frost heave is a serious concern in the northern region. So yes, it can absolutely be considered. It's just that how you quantify it is a challenge, right? You know how you will quantify this drop in serviceability just due to long-term effects is it's almost like you are giving a very logical guess. That's what it is. It's it's over 20 years. How can you say 0.8 delta psi? It seems almost unreal, right? But there is some kind of logic to it. But they have minimized the risk and accounted for it. If that makes sense. So right here, 11.20, I found the table, right? So right there, if you look at M values, so excellent within 2 hours, water removed within 2 hours, and the percentage of time exposed to saturation is less than 1%, your M value is 1.4 to 1.35. So you are really making the payment very strong, 35 to 40% stronger, right? So your M2 value now will be 1.4 to 1.35. Go on the other end, right? Very poor drainage, never drains, and water is saturated more than 25%. Right there, it has dropped it to 60%, by 60%. So it has dropped its capacity by 60%, right? So it really values that the water, it doesn't store water in the system. So I wanted to make sure that you capture that. So that table is 11.20. Any other questions? There are any questions in the text or any other questions?
Sir, in the equation that you have shown, that A1, D1, let us say corresponding to the asphalt mixes, there was no drainage coefficient. That means, let us say that was considered 1. Does that mean that asphalt layer has more capacity to drain water compared to other layers, but that is impermeable compared to other layers?
It's interesting that you notice that what they do is they are assuming that you will not hold asphalt, will not hold any water. You will drain them out right away because the air void is so low, around 4 to 5%, and you have very strong cross slopes. So the logic here is that you are not allowing water to be there in the asphalt. That's why M1, M is by default 1. But if you have any concern that the asphalt is going to hold water, then you should drop the M value, if that makes sense. But any stabilized material, they kind of assume that you will make sure that it doesn't hold water. Good observation.
So in that case, the M2, M3 correspond to the granular layers. So that the capability to drain waters, is it not from the top surface through rain?
The water could enter. You will have a transverse slopes, but you want to make sure that the water doesn't enter. And if it is entering from the top, the voids are so low that it is inevitably going to get top. So you will have water entering from different sides. You see what I'm saying? So you will have water entering from the edges, from other parts of the pavement, and you just want to build a layer that will allow the water to go through. Does that make sense? So, but you don't want the water to go through from the top. You want to have a cross slope to get the water out from the sides. But then water could enter from the sides into the lower layers, and that could be a problem.
Okay.
So right here, I think I covered this to A1, D1, minimum thickness. And right here, this does the same math for you. And it does that. And this is one of the example problems that we covered.
Sir,
Yeah.
sir, in the previous model, sir, AI model.
Yeah.
And this one is, sir, AASHTO. But this is not a model.
Correct.
So, sir, can you correlate it? Can you relate it for me, sir? Because there is completely different approach. Previous one was like NS and NR, and this is revolving around calculating essence.
Yeah. So it is.
So which one to use when, and which one is followed in US? The code follows which one method? Like
That's a very good question. So I mentioned earlier when the accelerated pavement testing was designed, they used the knowledge of mechanistic to design the pavement. They knew that a certain structure will have low stresses and strain, right? That was basic physics, basic mechanics, right? So mechanistic empirical directly is in the Asphalt Institute, that model. But it is indirectly by selecting the right sections and the way they interpolated from different pavement sections, they indirectly accounted for it, right? So I'm going to explain in my next lecture how they came up with the raw data and the nomographs. So all they're doing in that nomograph, it's in my, let me just go to the next. So this is what you're asking me. How that nomograph was developed, that multiple layers, how it was developed. And this was a very hard thing to find. I had to go through the original AASHTO reports for me to find this, because students were asking me this question. I'm going to cover that probably after the break. But like they really took some very basic raw data. I'm going to go down right here. Like I'm going to cover each of those. How was the empirical equation? How was this done? How was the original equation modified and why? I'm going to cover that. But then I'm going to cover each of those layers, what was included in there, right? I'll come back to it, but I want to explain something. And how they calculate the PSI in the layer. This is very important. I just want to give you this example right here. Look at the data. This is from the AASHTO data. This is the tracking data. Very crude. Develop the model and equation just based on a very crude fit. You know what I mean? And then when they go down, let me go down to the next layer. PSR, we will go to that right here. This is flexible pavement, right? And look at this 18 kip single axle, 5, 3, 4 are different axles. And look at the drop in serviceability index. This is raw data from the AASHTO, which is like we dug it out. And that's how they did 18 kip single axle. I'm trying to remember what 5, 6, 12 are. Oh, these index days are number of days that are below freezing. I think a number of days that are, I think that's what it is. And then you have rigid payment, you are seeing those drop in the P1. So they developed these models that you're asking me, the nomograph equations were based on these numbers. So you're asking me what happened in the AI and what happened in the nomograph. I'm going to explain this is how they came up with the nomograph.
But there also AASHTO has conducted those tests.
Yeah, AASHTO have conducted that. AI was developed based on AASHTO tests. So this is a very, I went in the end, sorry. I can start, we have time, right? How much time do we have?
5 minutes.
Okay, let's take a break and then come back. So I've covered this because this like these are the structures right there. This is the actual payment section right there. So I want to give you a little appreciation of what effort it took at that time in the 50s to develop this, right? And then look at this. I'll go through each of them, you know, what was done, and then right here, you look, they plotted E cells, W in the x-axis with P. They developed this equation, P is 4.2 minus 2.7. 4.2 is the start. This is raw data, this is not, and they fit it and they developed this P is equal to P naught delta P, and there is this coefficient right here. That's how the nomograph started to develop, that you saw that equation, one step at a time. But that's what you're asking me. Then for rigid payment, it went like this. So you have 4.5 minus 3 W over rho raised to beta. That's your first piece of the puzzle. Next slide. Then environmental and traffic side are not, they were not separated, right? Beta is a power which expresses the general shape of the curve. 1 is concave up, less than 1 is linear, greater than 1 is concave down. So that is going back to this, concave down, concave up. So just each of those factors now became part of the nomograph that people are using for the next 50, 60 years. Does that make sense? Go ahead.
This test was that conducted by AASHTO in the AI model, that segment.
Same thing, yeah.
This test is same and
Same, exact same.
they have conducted those like putting them in equations, and they have conducted and prepared this nomograph.
100%.
This is in this model.
Correct. So this is a statistical model. That was an empirical model. So this is just like, that's why I find it very fascinating for those people to do it at that level, right? Start from 4.2 and then how many repetitions? 832,000 repetitions was, they reached 1.5, right? So they kind of locked it, right? And then right here, curves become less accurate, very low PSI, and then they are looking at so there are some of the things that they noticed was what happened from 2.5 to 3.0 and stuff like that, you know. So right here, this is the actual equation, that nomograph. Log of 4.2 minus P for different sections. Section 306, one of the sections. Section 341, another section, right? They plotted this equation, right? Got the beta, right? And now L1, L2 is the configuration of the, I think it is in the next slide. There is, whether it is linear or not. So there are different parameters that are added, and then you are starting to form the nomograph equation. So it's just from simple data to delta PSI. So someone was asking me about the model, but this is really the groundwork of the AASHTO. And this I've taken just a snapshot, as you can see from those original reports, right? So section 306 of the AASHTO, section 341, and now they fit the data with the log drop in serviceability 4.5, and now they have different equations formed, and that became the nomograph that you are finding. This came from a question from my students, just like you are asking.